Good morning, this is Dr. Olson from Physics 1053 at Daytona State College. This video we're going to enter into Chapter 3 of our textbook. Now the first half of Chapter 3 is about vectors. You should have been able to review the vectors videos prior to watching this video. If you haven't yet, please stop the video right now, go back, do vectors, because vectors is absolutely critical from this point of the course on forward. So in this video, we're moving on into kinematics in 2 dimensions. Chapter 2 taught us about basic motion, position, velocity, acceleration, displacement, all of those. And also taught us about basic kinematic equations for one-dimensional motion. We're now getting into 2 dimensions here in this chapter. We'll start off talking about projectile motion. We'll also talk about how to solve these types of problems. We'll look at the shape of projectile motion being parabolic, and then we'll finish up with relative velocity. And then in a second video, we'll actually do an example of projectile motion problems. Okay, first of all, what is projectile motion? Projectile motion is basically any object moving in 2 dimensions under the influence of Earth's gravity. The shape below we see 2 figures here of objects moving in 2 dimensions. You can see being affected by nothing but gravity, their shape is purely parabolic. And that has to do with the fact that the only acceleration is downward because of gravity. I will show you that momentarily. So, since the only acceleration is downward, as indicated by the acceleration vector here in the center of the graph, that means that downward, just as we saw in chapter 2, you have an object that starts at 0, it starts to fall, its velocity in the y direction will then increase, going faster and faster in the y direction. Now let's ignore the y direction completely and just not pay attention to that. Let's say that this object also has a forward velocity vx naught. Okay, if it has that forward velocity, is there any acceleration in the direction of vx naught? The answer is no. Since there isn't any acceleration in that direction, then that component, the x direction of vx, velocity in the x direction, is not going to change. It's going to stay the same throughout the entire path of the projectile motion. So if you put them together, you have, to begin with, nothing but an initial velocity in x, and then a moment later you have the same velocity in x, but you now have a velocity in y because of gravity, giving you a total vector slightly downward. Moment later, vy is a little bit larger, which gives you a velocity even more downward, and then as the velocity in y increases, your total velocity vector increases downward in the downward direction. But the x component always stays the same in all of these cases. That's the basic idea of projectile motion, is now we are adding x and y components, with only the y being affected by acceleration of gravity. So key point that I hit on briefly, but I figure it's important to note. If an object is launched horizontally at some velocity v naught, then we can automatically separate and note that its initial velocity in x is v naught, because that's where it's going. That's the only velocity that's existing at the beginning at t equals 0. And your initial velocity in y is 0, because acceleration of gravity has not yet started to pull it down. That will change as time progresses, but when time equals 0, that is the case. Here's a fun little photograph showing 2 balls, the red one just being dropped, and the yellow one having some forward velocity v naught. So the photograph shows the 2 balls starting to fall at the same time, and notice that every time there's a snapshot, the balls are at exactly the same height. Every time they're at exactly the same height, which shows that yes, they are falling at exactly the same rate. It's just that the yellow ball also has a forward velocity Vx. Okay, so now we're ready to look at simple projectile motion problems. If you have an object launched at some initial angle of theta, then the horizontal component will just be, in this case, the cosine of theta times your initial velocity v naught, and your y component will be v naught times sine theta. So basically, in this case, when you have an initial launch angle of theta, you have to use your trig functions from our vector section of the course to determine the x, and, the horizontal and the vertical components. And then as we continue, it follows the same process. Your velocity in x never changes, but your velocity in y decreases as it goes farther up until you get to a peak where the initial velocity is 0. Or sorry, excuse me, not the initial. The y component of velocity is 0 at the peak, but x component is still forward. And then the y component of velocity starts to fall back downward because of acceleration. So how do we describe this motion? Well, we saw in chapter 2 that we can use these kinematic equations describing motion in either x or y. Well, the same story applies here. We can use the same equations for both x and y components completely independent of each other. So we can have one set of kinematic equations for x and another set of kinematic equations for y. They are the exact same equations, just used in different components. Very important notes here. Variables in the x direction will never be used in the y direction equations, nor will the y direction variables ever be used in the x direction equations. This is a common problem I always see. People are working with the x direction and say that acceleration is negative 9.8, which is wrong, because the negative 9.8 describes acceleration in y. Never put your x component variables in your y equations or your y component variables in your x equations. The only variable that can be used in both components is time. Okay, so when we actually do projectile motion, we already decided and saw that there is no acceleration in the x direction. But there is an acceleration in y direction, which is the acceleration of gravity being downwards, so negative 9.8 meters per second squared. So if we plug that in, say that acceleration in x is equal to 0, and Vx is now a constant, then your kinematic equations simplify drastically to that form. But your y component equations stay the same with just substituting acceleration in y with negative g. But otherwise your equations stay exactly the same. Now, to show that projectile motion really is parabolic, we have to remember what the equation of a parabola is. In algebra, you learned that a parabolic equation follows what's called the quadratic equation. Y equals ax squared plus bx plus c. I've just rearranged the terms here in this slide, but it is exactly the same equation. Now, this A, B, and C will depend on what the situation is that you are that you're looking at. In this case, we're talking about projectile motion, And so we can find an equation where we have an A, B, and C already substituted in. We've actually already learned that. Y equals y naught, a constant number, plus Vy naught times t. T is your single variable, plus 1/2 ay t squared. T squared is your squared variable. So in this case, t is your variable, y is the function. So indeed, this kinematic equation shows that, yes, projectile motion should follow a parabolic shape. In specific, in projectile motion itself, notice that yes, it is a parabola, but it's upside down. We're usually used to seeing a parabola with the vertex at the bottom. But in this case, the vertex is at the top. That means that the x squared term should actually be negative. Well, how do we account for this? Well, that's easy. Acceleration is negative 9.8 because of gravity. So that negative turns this whole term negative, giving us the upside down parabola. Perfect. All right, we're ready to finish up this chapter talking about relative velocity. In chapter 2, the textbook talks about relative speed in one dimension. Imagine somebody sitting on a train and somebody else walking on the train towards you at 5 meters per second. Well, how fast is that person moving? Well, relative to the person sitting on that train, he's walking towards you at 5 meters per second. But now let's say that instead of from the perspective of somebody outside or somebody sitting in the train, we're now looking at somebody outside from the point of view of somebody outside of the train. Train's moving forward at a velocity of 75 meters per second, while the person is still moving forward at 5 meters per second. How fast is he going from your point of view? Well, train's going 75, he's going with the train, plus he's going another 5 meters per second, which gives you a total of 80 meters per second forward. Now, this is a very simple example of vector addition. You have two vectors in the same dimension, just add the two vectors together, and you've got yourself relative velocity. Now I have to ask the question, which one is right? Well, they both are. The important thing is you have to define what your reference frame is, because without knowing your reference frame, we don't know how fast he truly is going. In two dimensions, we do things the exact same way, only instead of adding and subtracting values, we are adding and subtracting vectors. Now, this paragraph here is talking about an example we'll see in the next slide of a boat crossing a river where you're going to have three different vectors. Rather than say it in paragraph form, you can pause it here, read it if you want. I'm just going to go on to the next slide and explain it there. So we have the boat, which is crossing the water. So this is going to be the velocity of the boat relative to the water. A boat is just crossing the water itself. But if somebody's looking at the water from the stream, looking at the water from the shore, then they see that the current is flowing downriver. In other words, it's flowing at a velocity of the water relative to the shore. So here's the boat's velocity, here's the water's velocity. What is the actual path the boat takes? Well, you add these two vectors together and you've got the velocity of the boat relative to the shore. So yes, we do add these two values, but we have to add them as vectors, which means we have to use our trigonometric equations, Pythagorean theorem, and the sine, cosine, tangent trigonometry functions. So in summary, projectile motion is basic motion under the influence of gravity, creating a parabolic shape. And we can use the exact same equations we used in chapter 2, and relative motion has to be done by vector addition.